Hello, everyone. I'm Aditya. I work as a software engineer at Snap, where I work on compiler optimizations, software performance, and code size optimizations. Today, I'm going to talk about code size, compiler optimizations, and techniques for embedded systems. First things first, all the opinions expressed here are my own and does not express the views of or the opinions of my employer. To motivate the problem of code size, like why it is so important, and it has been getting increasingly important in recent years, especially if we consider mobile apps. The code size or the app size has direct correlation with number of downloads, because we can say that storage is cheap, but download may not be. People pay for the download in many places where Wi-Fi is not readily available. Also, if you consider the energy cost, this is not directly the cost to the app developer, but this cost is incurred somewhere. And even with a very modest estimates, just because the numbers of download are so high, you can say that just by saving 1 megabyte on each download would save a lot of energy. Now, as a software engineer who is sitting on the desk for 8 hours a day, I cannot go out and start planting trees, but I can save 1 megabyte on a really popular mobile application, which is essentially equivalent to planting like hundreds of thousands of trees. So I hope I have motivated the problem. TLDR is code size matters. Before digging into code size optimization techniques, I would first like to talk about how to measure those optimization. With any optimization, it is crucial to know like what we are doing and what is the impact. So there are popular tools, well-known tools like size, strings, and bloaty that can be used to estimate code size. This can also be deployed in continuous integration, so that when developers contribute code, we can see the code size impact of each patch. After that, I'll talk about compiler optimizations, some of the popular ones, and some of the compiler tuning flags. Then I'll share some of the insight into C++ library optimizations. Essentially, some of the optimization that, if done on C++, popular C++ libraries, can benefit that basically reduce the code size of application. After that, I'll talk about some of the source code techniques, like software engineering techniques, using well-known language features or code refactoring techniques, as well as some tools that helps reduce code size. And then I'll talk about how to get more insight into source code, like some instrumentation techniques that we can use to figure out like dead parts of the application and put some engineering effort there. And at the end, I'll talk about optimization that has not been implemented yet. And this is basically, that is one of my day-to-day jobs, like figuring out new optimization and contributing them to sometimes to open source or to internal version of the compiler. So as you can see, the flow of the presentation starts from like some basic concepts and gets more and more interesting. So when we talk about the popular tools like size, it essentially gives you a very high-level overview of the code size, like text section, data section. String tool basically gives you lists out all the strings in the binary. They can be string literals or some function names, etc. And the third tool sharing here is bloaty. It is shaped by Google. It gives you more finer grained analysis of code size. So it helps redirect focus on which part of the section, like binary, we want to put more effort. As a case study, we want to look at how using a very basic tool like strings can help us figure out like code size opportunities. So when we run the string tool, it basically gives you string literals, some function names, and all the error messages. Those are also there. As an example, when we run the string tool on lib standard C++, it has like more than 2,000 strings. And one example is like attempt to splice a list into itself. We might wonder like where this is coming from. And the easiest way to figure out is do git grep in that repository. And that file is debug.cc. As someone who is not an expert in lib standard C++, I may start to wonder like why debug.cc is shipping into a production code. Now, there might be a valid case, but this still gives me a useful direction to start investigating. Moving on to popular code size optimizations. First, I'm sharing the popular ones, which are like very well known. You might already be using it if you care about code size. The first one is -os, which literally tells the compiler to optimize for code size. The second one is FLTO. This optimization, this is basically a link time optimization where at a very high level, what it does is it puts all the translation units together and runs the compiler on that. Because of better visibility, the compiler can reason more about the entire program, and all the interprocedural compiler optimizations, they run very effectively. And many of the functions get inlined, many of them disappear because of the visibility rules. Many of the global variables basically disappear. By disappear, I mean optimized away. The third option is --strip all. This is a flag to linker to remove the debug section. We might just remove -g from the build rules. But what happens is in any large project, it is basically a collection of several small projects, right? And some of the projects may be third party or open source, and all the separate sub-projects may have different build rules. We cannot go and start editing the build rules because that may create maintenance overhead. So at the top level of the build rule, we can just pass --strip all, and it will essentially do the same thing. The fourth one is fno unroll loop. This is a very specific flag for like very specific optimization, loop unrolling. Loop unrolling is a performance optimization. It increases code size depending on the mood of the compiler. Basically, some compiler may unroll like the full loop like completely, and it incurs a lot of code size overhead. The next one is -fno exceptions. This flag instructs the compiler to not emit exception handling code when there are basically no exception handling. There are no uses of exception handling. Like if you do not have throw statements, and so there is basically if you do not care about exception handling, then you don't want the extra code to be there. And there are of course nuances that sometimes the compiler may give you error if you have exception handling code and you pass fno exceptions. But in many applications, the exception handling code itself is not there, and the compiler will still generate a lot of like stubs for runtime exception handling. Similarly, -fno RTTI instructs the compiler to not generate runtime type information, all those for all the virtual classes. This is also helpful because it reduces code size. This may not reduce by a lot, but it is still useful to know. Some of the compiler optimization, they they help in some code bases, but they increase the code size in some code bases. One of the typical example is -f function sections. What it instructs the compiler is to generate each function in a separate section. Okay. Now, and when the linker sees that every function is in a separate section, all the sections which are unreferenced get dropped. That removes a lot of dead functions. So conceptually, it seems that this should reduce the code size, and it does in many cases. But what happens is, because each function is in a separate section, there are overhead like alignment, and some globals are also basically not as optimized if all of them were in one section. So that overhead has to be less than the number of functions removed. So you might want to try, and if it helps, great. If it doesn't, then you want to remove this flag. Similarly, -f no jump tables. This instructs the compiler to not generate jump table for switch statements, and instead generate a switch statement as a sequence of if-else statement. In some cases, it helps with code size. In some cases, it doesn't. Some compiler flags are specific to compiler. Like these flags are specific to GCC. -f inline small functions instructs the compiler to inline only small functions, because inlining small functions reduce code size because of the overhead of call and restore. Similarly, the second and third function are so second and the third flags are essentially similar: -m call prologues and -m save restore. What they tell the compiler is to outline the call frame setup and restore instructions. So in all the functions that are generated by compiler, in the beginning of the function, there is a like standard set of sequence of instructions. Those are required to respect the calling convention. You might want to go and read more about it if you are interested. And similarly, there is a set of instructions at the end of the function to restore the call frame. These flags, what they do is they ask the compiler to not generate those like setup and restore. Instead, make a function call to the runtime, like libgcc. And those runtime functions already have those sequence of instructions. So essentially, it saves a lot of code size. It, of course, incurs performance overhead. The fourth one is -f live range shrinkage. And the fifth one, F reorder basic block algorithm. These two are basically, if I can say that, these are slightly complicated flags, and you don't want to go and do them like right away. Basically, these are flags that change the strategies of the internal compiler optimizations. The live range shrinkage asks the compiler to reduce the live range of variables, and that helps with the register allocation. So register allocation will have less spills, and each spill incurs code size. The next one, reorder basic block like blocks algorithm. It basically instructs the compiler to change their strategy of reordering the basic blocks. And the simple algorithm has minimum code size overhead. The next set of flags, which are compiler tuning flags, are specified with --param prefix. These are like magic numbers, if you will. These magic numbers are basically cost models to help compiler make certain decisions, like how many functions to inline, what should be the overhead of inlining before, after the inlining has happened, what is the total size of the translation unit after a certain number of inlining has happened, things like that. And I've listed like 6 of them here. These are, they provide code size tuning flags, tuning cost models. These are the ones I've listed are default of GCC, I think GCC 10. You might want to try them, but these are not the flags you want to go after them first. These are like you want to go when like other options are exhausted. Certain flags are like non-compliant, like -f merge all constants. This flag basically it's a very aggressive optimization. Let's say there are two constants which have the same value, and compiler can do optimization where both the constant points to the same address in the memory. Similarly, -m int 8 basically tells the compiler that all the integers in my program are basically less than 8 bits or equal to 8 bits, their values. These are language non-compliant, of course, but if your application satisfies certain requirements, by all means, go ahead and do them. If there is an error, debugging the issue will be like a big nightmare if you have flags like these. Similar to GCC, LLVM also has certain flags. For example, the first one is -oz. -oz tells the compiler to do aggressive code size optimizations. GCC does not have -oz, it has -os, just like LLVM. The thing is, -oz of LLVM and -os of GCC, one cannot say that one is like better than other in terms of code size. It is totally possible that -os of GCC gives you smaller code size than -oz of LLVM. It may depend on the application, and you might change the tuning flags of one GCC versus LLVM to achieve similar results as well. The next one is thin LTO. This is specific to LLVM as far as I know. When we do the link time optimization, where all the translation units are put together, the compile time rises dramatically because some of the algorithms, they are like quadratic or like non-linear at the least. For example, like the inlining algorithm and a certain interprocedural optimization as well, like function merging. These optimization incur not only like compile time, but as well as like memory footprint. And because of that, it is not possible to compile large applications. Like in some cases, it is not even possible to compile, like system crashes sometimes, or it might take like hours and hours. So thin LTO gives you a nice compromise. It will achieve like 80% or like 85% of what full LTO does, but the compile time will be like dramatically low. By dramatically, I don't mean like an order of magnitude. It might like reduce by half or something. The third one is identical code folding. Basically, this optimization enables compiler to merge functions which are like exactly the same, or like even if they are a little bit different, basically the compiler can insert like if-else statements or add additional parameters, and functions can be collapsed. GCC already has this optimization of identical code folding, but LLVM's optimizations are not enabled by default. -f merge function is available already in LLVM trunk, but you have to enable by passing this flag. But enable merge similar functions, this is not in LLVM yet. It has been in review for quite some time. The next two optimizations, GVN hoist and GVN sync, these are the optimizations which are basically collapsing similar instructions. They provide like minor decrease in code size, like it could be like less than 1%. The next one is machine outliner. This is a very aggressive code size optimization. It can give like upwards of 10% in many cases of code size reduction. But what it does is it outlines certain code sequences, the code sequences which are found in many other functions. And because of that, it gives you like massive code size reduction. Next one is hot-cold splitting. This is again similar optimization is available in GCC as well. This optimization splits a function into basically hot and cold. The cold pieces of function, cold means the parts of function which are not executed very frequently. They can be outlined into a separate function. And coincidentally, the smaller code sequences, like the cold sequences of code, are quite common, like can be found in many other functions, like let's say assertion failure messages or catch block of C++ function, catch block in C++ functions. They are quite identical in many cases. And when we outline them, they can be collapsed. And the last one is playing with the inline or threshold, similar to what we have in GCC dash param. All right, moving on to C++ library optimizations. Popular C++ libraries like standard libraries or like Boost, Eigen, etc. And they have a very common pattern. And the pattern is that most of the functions or utilities are defined in header file. It has their advantages, I agree. But a side effect is code size. All those templates, they get instantiated in every translation unit and incur code size overhead, compile time overhead, etc. You might say that those functions are basically deduplicated by linker, because only one definition will remain if for a certain type, right? But what happens is those functions get inlined in many cases, like the smaller ones at least. And those inline code is not going anywhere. You must incur that code size overhead. By explicitly instantiating for common types at least, you reduce code size, you save a lot of compile time as well. Unfortunately, it is not always possible, or not possible easily. Like if you want to try instantiating vector of int in a translation unit, and then you'll have a lot of fun. Another thing we can do is to mitigate the effects of all this definition in header file is adding attribute no inline to those function definitions or declarations. Sorry. This instructs the compiler to not inline those code, even if it is profitable to inline based on some compiler heuristic. And this kind of mitigates some of the code size issues with the standard libraries. Again, you have to go and edit those source code, and which is not always pleasant. Moving on to source code level optimizations. I'll talk about 6 different techniques, and I'll try to go through them slightly quicker. First one is code refactoring, then source code annotations, then moving on to more interesting ones like cheaper data structure and algorithms, and then using certain standard library routines and tools that can help reduce code size. So the first one is using like code refactoring techniques. Most of what I've listed here are like very well known, like moving functions out of header file for the reasons I said before, moving classes out of header file if we don't need the definition in the header file, just move it out. Global variables, they are always, like most of the time, they are a bad idea. And in header file, it is like even worse. Flattening classes. In C++ or like in most object-oriented programming, developers get into habit of defining like hierarchies after hierarchies. Sometimes when it's very common to see that when we import or start using a third-party library, the first thing developers would do is start writing wrappers around those interfaces and then use those wrappers. Of course, it has software engineering benefits, but it incurs code size. Like you have all those abstraction penalties, right? So removing those useless hierarchies, like flattening class hierarchies, they are quite helpful. They also make things easier to read. Let's say I already know Boost library, like some parts of Boost library. But if someone defines a wrapper around Boost library, I probably wouldn't not even know that internally that thing is using Boost library. So I have to, it's like a mental overhead on my part. The next two, like early evaluation and lazy evaluation, are basically similar in spirit. What I'm trying to say is moving the code, moving the like computation or evaluations out of the binary. Like when we do early evaluation, like some of the functions just disappear because of the compiler optimizations, right? And when we do lazy evaluation, what I'm trying to say here is basically instead of generating the code in the binary, we do code generation or some form of code generation at runtime. A typical example would be like a very simple example would be, let's say we have like thousands of classes where they have a method like, let's say, get name, and all they do is that they return a string, some kind of name. Instead of having all those like thousands of functions to do that thing, what we can have is, let's say, a hash map of a pointer or something, and like an array of strings, and then we can construct similar things at runtime to achieve similar behavior. It may have runtime overhead, but the binary size will reduce, that which is our goal here. And most of the time, runtime overhead is as like overstated. Like sometimes those functions never get called. So we are just getting code size for free. Explicitly generating definitions. These are like basically taking advantage of language features. Like with newer version of C++, we have like a lot more constructors, and we have like rule of 3, 7, and depending on how many types of constructors you want or you have defined, or like how much you have messed up the rules of like 3, 7, compiler will give you definitions for free. And many of the times those definitions will be in all translation units. They'll get inline, incur code size overhead, etc., etc. So a good strategy is to explicitly instantiate in a CPP file, like either default instantiation or your custom instantiations, or maybe delete those definitions, like equals delete. Either way, they are much more beneficial compared to like not like just relying on compiler to do implicit definitions, which may have a lot of code overhead. And similar to the constructor destructors, we also want to instantiate templates if possible. And certainly for like well-known types, let's say, even if the classes are generic, but they are not used for all kinds of types possible, right? Some of the types are like way more used than others. So we might want to do explicit instantiation of like commonly used types at least. The next one is reducing inheritance like as much as possible. It is not uncommon to find like virtual functions like everywhere. In certain code bases, like people would have written virtual just because, I don't know, they wanted to. There might not be any like a good reason to have virtual function, and they incur code size overhead because they emit those runtime type information for like dynamic polymorphism. Another strategy is to take advantage of empty base optimization. In cases like where getting rid of hierarchy is not possible, but it could be possible to move the like member variables out of the base class and put them in derived class. So only those classes which need those variables will incur the code size. Others will take advantage of the empty base optimization. The third one I'm talking about here is moving member functions to free functions. Like not always, of course. What happens is like when developers are writing code, and if they see certain code that are similar to what they want, they will blatantly copy from one file to another. Now you have two copies of things which are like similar. Instead of doing that, we can move those member functions out as a free function so that multiple places can like reuse the same function, right? Compiler helps in certain cases here, like identical code folding basically relies on this behavior, where and that is how it gives you massive code size wins. Certain attributes help compiler to make like educated optimization decisions, like attribute cold and attribute no inline. They instruct the compiler to basically, like attribute cold tells the compiler that that particular function is cold, like it is not used by performance critical parts of the program. So we don't need to have aggressive code size, aggressive performance optimization there. And attribute no inline will basically disable inlining of that particular function. These are basically, you want to do this for very specific cases because they affect readability and increase maintenance issues. And pragmas are, like, you almost always do not want to do pragmas unless and until like you really need them. Like pragma pack and pragmas to instruct compiler to do certain optimization. And the third one is pragma clang push. This is such a long pragma that I cannot even read in like one go. So basically, I'm trying to emphasize that these options are possible, but you are better off not doing them. Moving on to another source code level optimization. This is interesting as well as slightly controversial. In C++, the default data structure we use is vector, right? Vector, sometimes dec, but mostly vector. And similarly, with a recent version of C++, we use unordered map, unordered set, way more than map and set. But why do we use them? For performance, I think, right? What if performance is not the most important criteria? What if code size matters more in many cases, right? For user-facing applications, like we are not counting like microsecond. We are in like millisecond and second territory, like hundreds of milliseconds. So in many cases, performance is just overrated for mobile application. So instead of vector, which has higher code size overhead, we can use like list array. Similarly, std map and std set has lower code size overhead. Now, I'm not if it appears that I'm suggesting you start removing vector and replace with list. That is not my suggestion here. What I'm trying to say is motivate here is the thought process. Like just because certain data structure is used because of like popular opinion, that does not mean that we should use them. Like we should look at the requirements of application. Like let's say performance is not the most important criteria, then we should choose data structures which are cheaper, or they are more suitable for our requirements. Like for example, list or array in this case. Similar, this is an example. It is a very synthetic example to show that map and unordered map, similarly list and vector. Vector has slightly large code size overhead, and map has slight unordered map similarly has a slightly large code size overhead. This is a very synthetic example, but this motivates the point that certain data structures are more suitable for certain kinds of requirements of application. So for code size sensitive application, we can choose to have cheaper data structures. It is possible that for a large applications, those methods of vector or unordered map, their overhead gets amortized over multiple functions, right? But what if your particular application has certain custom data structures, maybe not vector, but some other data structure that are getting widely used because of popular opinion, right? We don't have to use them if there is a better, cheaper alternative. Similar to using cheaper data structure, that analogy translates to using cheaper algorithm as well. And again, I'm choosing a controversial example to motivate the point. But more importantly, I'm trying to motivate the thought process that we should not use a certain data structure or algorithm just because everyone else is using them. I guess, in my opinion, the requirement of application are more important. We see here quicksort is the most popular sorting algorithm, and it has rightly so, it has a time complexity, average complexity of n log n. Bubble sort, it is much shorter in terms of code size, but it has performance penalty, quadratic. Now, what if performance was not the most important criteria? Why bother using quicksort? Quicksort, if you want to go and look into the implementation of quicksort in standard libraries, they are basically unreadable. They are so big. I know because I optimized one of the quicksort algorithms. It has not been accepted, so don't start going and doing git blame on that one. Bubble sort is very tiny for loop, a couple of for loops. Here is a small mental exercise, right? Quicksort has average time complexity of n log n. And linear search, let's say we do not sort the sequence at all. Linear search has time complexity, average time complexity of O of n. Now, if we only need log n searches for that sequence, let's say we have profile information, it says on an average we need only log n searches. Then instead of doing quicksort and binary search, we are still better off with linear search, right? And because of all the overhead of extra code, you might want to give few more searches for linear search for free. So, this basically motivates the point that linear search is not always a bad idea. It has much easier readability. You don't have to schedule sort sometime before in a cold section of the code, right? The sorting should not be on a critical path, right? Because if sorting becomes overhead, then again, that is a problem. Binary search is only useful when you have already sorted, doing quicksort or something, or bubble sort. In some cases, sorting is if you're successful in moving sort out of performance critical code, then why bother doing quicksort? It is not performance critical, so it just do bubble sort, right? So I'm basically trying to basically instigate different angles of thought process to why should we use a particular algorithm or a data structure, and this thought process basically will help analyze different approaches and making a right decision based on the requirement of application, not because it was a popular opinion. Okay, moving on to certain C++ or C library routines. We all want to write a lot of code. For loop is we just write out of Vim sometimes. You see here on the left-hand side, it's a very tiny for loop. At OZ in Clang, it will generate around 10 instructions. But it is essentially a memcopy. So if we choose to do memcopy, then we have only 3 instructions in the final assembly. So it is a massive code size reduction. And we are using a standard library, which is highly optimized. In many cases, compiler cannot do that kind of optimization. And this, on the left-hand side, this for loop is at OZ, the code generation. If you do O3, This is such a regular loop that the compiler becomes really happy and starts doing all kinds of optimization like loop unrolling, vectorization, and the code also becomes very unreadable. But on the right hand side, even at O3, it will give you the same 3 lines of code, and it will probably be much more highly optimized. There are certain tools that help with code size reduction. Like we can play with the, let's say, the build system, the rules of the build system to split out a binary into like the main binary and a shared library. Now the final code size may not be the same, may not be smaller, of course, but the main binary is smaller in code size, which is very helpful. It helps with the launch time of application because the working set would have reduced. Another advantage is because now we have put certain code in shared library, they can be compressed and loaded at runtime. These they give like massive code size reduction, but you really want to do this if code sizes become like really painful, because it has performance overhead. Some of the systems would not like all these tricks that you play, like you decompress a blob and load as a shared library. It might have security issues as well. But certainly this is possible if the code size is becoming a lot of problem. In certain applications, it is common to ship the debugging code as well. So you want to compress those debug sections using popular tools like libelf or elf compress. Similarly, we can strip the symbols out of the final binary. Symbols are not really needed to execute the binary. So popular tools like strip from binutils or LLVM strip can be used there. This is a very interesting approach where we use compiler instrumentation techniques to learn about the code base. In any large application, there will be a ton of dead code. It could be because of the legacy code, third-party libraries. It could be because of the development style. It could be because certain developers were working on a particular feature. They wrote a ton of code and they moved to other project or left the company. And those will still end up shipping all those dead code to production. How do we figure out those dead code? It is almost impossible for developers to go and read all those like millions of lines of code, right? So here is a strategy. What we do is we instrument each function, like the entry of the function, that the second flag here, f instrument function entry bear, and put like dedicated counter to each function. And we deploy this application to certain, certain system. When we say we deploy, means I'm not saying that I deploy at my employers. I'm just giving a strategy here. Over a long period of time, we'll find out what functions were called. And the functions which are not called, we can look at those. If they are not called, that doesn't mean they are dead, of course. That there might be exception handling routines, and we'll have brightest engineers, so they never got called, right? So they were just careful. But it certainly reduces the consideration set like by orders of magnitude. And now we can deploy engineering effort to look at, like even manually look at those functions and figure out if they are dead or not. They're like quite helpful. It helps with code size. It helps with maintenance overhead as well. This is the last section. It's quite interesting, at least to me. I'm talking about optimization that are yet to be implemented in standard library or in compiler like GCC and LLVM. For the C++ standard library, I'm talking about one particular optimization where we can add no except, like conditional no except to as many functions as possible. This is a function like vallocate, which is called by the constructor of vector. So you can imagine how popular this is. This function throws, if you see the conditional, like if the the number of allocations are more than certain size, basically the vector cannot allocate, it will throw length error. Now, in many applications, we really want to just crash the application if there is an error. We don't want to recover, and certainly not when memory allocation has failed. The application is already in a state it's almost impossible to recover or reason about the whole entire program in any sane way. So we might better just crash. And certainly for non-mission critical software, like let's say a mobile app, it crashes. It's okay. It's not too bad. So what we propose here is adding no except with a conditional, and that conditional can be used by the build rules. Like let's say if that conditional is a macro, we define that macro via build rule, and basically parts of application where we do not care about exceptions, the compiler will not generate all those ton of exception handling, like all those runtime stuff, right? All those landing pads, etc. They are just pure overhead for certain applications. Next one is a set of optimizations that are not implemented in like GCC and Clang, as far as I know. The first one is it's a very useful trick. Basically, what I'm suggesting here is the compiler can kind of hash the body of the function. Let's say there are two functions which does exactly the same thing. Then we can hash the body of the function and put the hash as the name of the function itself. Let's say in our case, the hash comes out to be f returns 10. Because the name of the function are exactly the same, the linker will deduplicate the function names, and basically only one definition will remain in the final binary. This will give code size reductions. There are optimizations like identical code folding, which achieves similar things, but that optimization is not linear because of the strategies used there. This is a much trivial optimization, and it is linear because we're just traversing once and renaming the function. It is not as trivial as it sounds, but basically it can be done. Second one is aggressively outlining of cold regions. As I mentioned earlier, hot-cold splitting optimization, which I implemented in LLVM, that is similar in GCC. They mostly target small code sequences like basic block or only a few basic blocks. What we can do is we can start outlining aggressively like larger and larger regions. And because of that, when we outline larger and larger regions, it is possible that those are basically those are cold, no doubt about this. We put them in a separate library or separate section. We can also deploy like merge function or identical code folding on those code blocks, right? And they help reduce the code size quite a bit. The third one is merging of similar functions. I briefly hinted at this before. In GCC, I don't think there is any optimization like this. On LLVM as well. In LLVM, however, it has been proposed multiple times historically. Like you see the differential number, the first one is 22,000 something, and the second one is like 111, so 1,000. So it was proposed recently over a span of like 5-6 years. They have not been accepted. They are still in review, and it'll be really useful to get them in the main line of the compiler. They help like reduce the code size massively, like more than 5% or maybe more than 10% in certain cases, like depending on how much C++ templates you have used. So it really helps. These are certain optimizations which are not in LLVM. Most of them I have hinted before. However, I'll briefly talk about the last one, loop idiom recognition, because this is a very common optimization that we should have in LLVM. But LLVM has loop idiom recognition. It does recognize memcopy and memset, but only for like very trivial cases. Like let's say you're iterating over a array of char. And in those cases where memset and memcopy will be recognized. But if we are iterating over an array of integer, like let's say we are assigning one integer array to another, it's a very common pattern. And integers are like, it is much more common to iterate on array of integer than array of char, in my personal experience. So why is Clang not recognizing them? Well, GCC does, and here's a link to Godbolt if you're more curious. And that's about it from now, from my side. There are many more resources online. Here are only a few which I found them useful. The only one I want to call out here is the GCC manual page. They have a lot of optimizations and nice documentation, so you can go and read about them. I believe a few years ago, there was a similar talk at CPP Now, -OS Matters, and that is also very useful. You want to check them out as well. Thank you. Yeah, we have a couple of questions in Zoom. I'll answer them. First one is, isn't it better to use flat map instead of map? Depends on your implementation of flat map. If it reduces code size, and yeah, by all means go ahead. What I'm understanding is, I think you're suggesting that flat map is a better in terms of performance compared to stud map. Yeah, by all means go ahead and do that. My criteria was to basically show that there are cheaper alternatives in terms of code size. So totally go ahead. Yeah. The second one is, why doesn't the compiler call the same mem copy? Which is in the last slide I briefly mentioned. GCC does in the example I mentioned, but LLVM has yet to implement that optimization. It shouldn't be too hard to do that. Next question is using shared objects in your experience increasing or decreasing the overall binary size? So yeah, when let's say we have a binary, like one main binary, and we split them into shared objects, it could increase the code size for sure. However, there are benefits that now the main binary becomes smaller. So at runtime, the working set, which is some measure of size, can reduce. And again, I think I briefly mentioned that in the shared binary, which is not the main one, right? We can compress some parts of the binary. So that way you can get much less code size. Of course, it's not trivial and there's a lot of other issues, but it becomes possible to compress the shared library. Yeah. No, there's no open questions. Yeah, I don't think there are any more questions. Yeah, okay, there's one more. On your last or second last slide, you mentioned deduplication of sibling branches path as an existing optimization. Don't LLVM do that? One second. Deduplicating of sibling branches. Yeah, so I have attached the, GVN hoist does not do that. The GVN hoist basically will deduplicate like identical instruction and hoist them to one of the parent basic blocks. And GVN sync does that in the opposite direction. Of course, hoisting is much more possible based on my experience. You can sync, but not many instructions are syncable. The example that I think I have the bug number in the slide. Otherwise, I can share with you if you message me privately. That example is not done by GVN host or any. There are many other optimization in LLVM. None of them do that.